Okay, so I'm here doing some example problems from homework number 5, and hoping this is useful to you as you study for the exam. Um, and here's problem number 1. And in problem number 1, we're given an asynchronous link. And an asynchronous link in this example sends a byte as 8 bits in a row with a start bit and a stop bit. And what we're doing is we're looking at uh, the timing of these bytes. And so what we're going to do is we're going to draw this picture of these bytes going by in time, and we're going to label this as the time axis. And this is going to be then the pictures shown here are going to be the bytes as sent by the transmitter. So this is the period of a bit as sent by the transmitter. So that's TTX, and that's equal to 125 microseconds here. And 125 microseconds is 1/8,000th of a second. So this is an 8 kilobit per second link. Okay, and what I'm going to do is I'm going to draw the sampled bits with these arrows. And so what we're going to do is we're going to draw the time at which the receiver samples the bit with the arrow. And ideally, say in case B here, as shown in the homework problem, in case B, the bits are all sampled exactly at the center of the bit period, which is the best place to sample them. So ideally we have this situation where the clocks of the transmitter and the receiver are perfectly in sync. Okay, but there are a couple cases where it can be out of sync, and in the first case, the clock of the receiver is a little bit shorter, is a little bit slower than the clock of the transmitter. And what I've done here is I've shown that receiver clock being a little bit slower and having a slightly longer period. And you can see here now that we've sampled 8 times, 1, 2, 3, 4, 5, 6, 7, 8, but that by the time we hit the 8th sample, we are at the edge of a bit period. And sampling at the edge of a bit period is no good, as we know from looking at the eye diagrams. Okay, and part A asks you to calculate the bit period and clock rate for case A, assuming the transmitter's clock rate gave a bit period of exactly 125 microseconds. What percentage wander does this represent? Okay, so we're interested in the bit period of the receiver, which is slightly longer than the bit period of the transmitter. And we can calculate it by looking at this picture and assuming that this picture is a scale diagram of time. And so for part A, what I'm going to do is I'm going to start here in time, and I'm going to end up here in time, and I'm going to count how many bit periods that is for the transmitter and how many bit periods that is for the receiver. And you can see for the transmitter it is 1, 2, 3, 4, 5, 6, 7.5 bit periods of the transmitter. However, it is 1, 2, 3, 4, 5, 6, 7 bit periods of the receiver. And so 7.5 times the bit period of the transmitter is equal to 7.0 times the bit period of the receiver. And we know the bit period of the transmitter, so we can solve for the bit period of the receiver. And it's 7.5 over 7 times the period of the transmitter. And this is 15 14ths of 125 microseconds, which comes out to be 133.3 microseconds. Okay. For part B, it asks you to calculate the bit period and clock rate for the case C. Oh, first of all, in part A, let's calculate the percentage difference. The percentage difference is about 1/15, which is about 6%. I'm not going to do the calculation in detail. For part B, it asks us to look at case C, and case C is the case where the receiver clock is a little bit faster. And so we're going to start off, we're going to assume we're going to start off in sync here, and it's going to be a little bit faster, and so you can see that the samples get a little bit closer to the edge in the other direction, and I'll see if I can draw it here for completeness. And there we have the samples of the receiver. And so I'm going to do the same thing. I'm going to start counting at this midpoint here, and I'm going to end at this point now. And I'm going to say that this is 1, 2, 3, 4, 5, 6, 7 times the bit period of the receiver, but it's also equal to 1, 2, 3, 4, 5, 6.5 times the bit period of the transmitter. And I can go ahead and label these things up here also. So I have 7.5 T, TX, and I have, oops, this is going to be 7 times TRX. Okay, and so I'm going to do the same sort of calculation. I'm going to say that the period of the receiver is equal to 6.5/7 of the T of the transmitter, which is equal to 13/14 of 125 microseconds, which is equal to 116.1 microseconds. And this represents an error of 1 part in 14, which is about 7%. Okay. For part C, it asks you, does this problem consider the effects of clock jitter? Explain. And the answer is no, jitter is not considered here. Just wander. And you can see that in this example, the bit periods are all assumed to be exactly equal in time for either the transmitter or the receiver. We're not considering the effects of jitter here. So, hope that helps on problem number 1. Thanks.